Okay, I think we can begin. We are almost 200. So welcome to week 14 of AI504. So this week we'll be covering deep diffusion probabilistic models, or DDPM. So this will be a new content compared to last semester. TA has to say something? All right, so if you haven't, please check yourselves in. TA has just shared the link, attendance link. So today's topic will be generative models recap. Actually, let me just put on my earphone. I'm sorry, I think I lost my earbuds. Can anybody hear me okay? 다 잘 들리시나요? 제가 지금 이어폰을 못 찾아가지고 지금 그냥 그 마이크로 하고 있는데요. 네, 좋습니다. All right, so we'll continue. So we'll have a short recap, and then we're going to talk about DDPM, deep diffusion probabilistic model, then move on to deep diffusion implicit model, which will be a bit more advanced, not advanced, but a bit of a more generalized version of DDPM. And then we'll be going into conditional models, which are called classifier-guided diffusion. Actually, there's also classifier-free diffusion as well. So classifier-guided includes classifier-free diffusion. So two types of conditional models. And oh, by the way, if you haven't downloaded the material, please go to Classum and then download now. I uploaded it like maybe 30 minutes ago and an hour ago. All right, I'm going to have to mute everybody. Right. So today there are a bit of material today, and I'm not sure if I can cover it within an hour and a half because there are like 50 pages of math, all mostly mathematics stuff. So I'll try to cover it as fast as I can. And but if you have any question, just ask away anytime, because you don't need to actually remember and memorize all the mathematical detail. Question from Ihe. There's a campus-wide UG admission this Thursday. Is our class going to according to plan? UG admission? UG admission이 뭐죠? undergrad, 학부생 입학인가 보군요. 학부생 입학이 저희 수업이랑 상관이 있나요? 잘 모르겠는데. 원래 그 목요일이 수업을 안 하는 날로 지정돼 있나요? Anybody? Is it an official off day this Thursday because of the undergrad application day? No, I don't think there will be an off day for this course, because this Thursday you'll be practicing DDPM, so which will be a very important step for probably everybody. So hopefully I hope that nobody misses it. Right. So generative model recap. So there we covered at least 3 things so far. So VAE, we covered VAE. So there was encoder and decoder, and then the encoder tries to encode your sample into a Gaussian distribution, that looks like this. And then the decoder will sample from a Gaussian distribution and then reconstruct it back to the original sample. So that's the VAE. There's also, well, we haven't officially covered it, but there's also something called flow-based models, like normalizing flows and glows and like real NVPs and that kind of stuff, which kind of like addresses the limitation of VAE, because if you think about VAE, there's a disconnect between the encoding process and the decoding process, even though the two are connected by this constrained distribution, which is usually a Gaussian distribution. So, but there's a disconnect, meaning that the encoder has a parameter theta and the decoder has a parameter phi or phi. So they are actually 2 different functions. So there's no guarantee that this sample and this sample will actually be in the same. Well, I need to. So this sample and this sample, even though they're the same samples, there's no guarantee that they will be placed in the exact same spot in the Gaussian distribution, because the encoder is modeled by Q theta and decoder is modeled by P phi. So there's a disconnect. So flow-based models actually address that. So they use a sequence of invertible functions to map your original data into a latent space, usually Gaussian distribution, and then inverse function, a sequence of inverse functions will actually reconstruct it back, or put back, or map it back to the original data space. So there's now no longer a disconnect. It's actually there's a consistent mapping between X and Z. So it overcomes the limitation of VAE, but it has kind of a limitation in its own respect, which is that you have to use invertible functions only to guarantee this kind of consistent mapping. And because thanks to this consistent mapping or invertible functions, you can actually train this with direct log likelihood maximization. Here you had to use variational inference using variational lower bound or elbow. Here you don't have to, because you're using invertible functions. So you can directly optimize the log likelihood. Then came GAN. So we learned GAN as well. So GAN also is another form of generative models, or actually you can just all think of these as like sampling functions, or neural samplers. So GAN has its own architecture where you have a generator and discriminator, and the discriminator's job is to just discriminate whether the given sample is from the generator or from the real samples. And the another thing that we talked, not officially, but briefly on while we were talking about RNNs and also talking about transformers, we talked about autoregressive models. So all these are autoregressive models, and this is another way to generate a sample, in a sequential manner. So then diffusion is a whole different stuff. So far we've talked about VAEs, flows, GANs, and autoregressive models. And diffusion is, you can think of diffusion as like a sequence of VAEs, or like a multi-step VAE. It has the most analogy to VAEs. And the high-level idea is that high-level idea is that you start from your known sample X0, and then you gradually add noise to here, until all you're left with is complete noise, actually, XT being usually just some sample that is from standard Gaussian distribution. So this would be the forward process. Adding noise is the forward process. And what you want to do is you want to reverse it back to the original. You start from the normal distribution, and then you want to somehow denoise your sample all the way back to the original sample space. So that would be the reverse process. And turns out it works very well. All the state-of-the-art text conditioned image generators like DALI 2, Stable Diffusion, what else? Imagen, like all these are based on diffusion models. So we'll be studying that today. There's a very nice overview. Actually, I highly recommend that you visit this blog here. It's very well organized. It just tells you everything you need to know about generative models, and especially the diffusion diffusion page is very well thought out and well organized, and has a very nice comparison to begin with. So there's GAN, there's VAE, there's flow-based models, and then there's diffusion models. Well, I mean, we're missing autoregressive models here. All right. All right, moving on to DDPM now. So I talked about forward process and the reverse process. So forward process is keep adding noise to the original data. So your data is X0, which comes from the P data distribution. And you keep adding noise until your XT looks like some sample from a standard Gaussian distribution. And you do it by keep adding your noise theoretically to the infinity. So if you keep adding like very small amount of noise to your data, like you can see that here, it's already a bit, there's a bit of like level of noise already into the data. But if you think about putting very, very small amount of noise, then like it's almost like, indistinguishable between a original sample X0 and some sample which would be X1, which would be very, very small minuscule noise here, then it will be almost indistinguishable. So if you keep doing that, and then you will eventually end up here. The reverse process is obviously you want to. So the whole idea behind generative model is that you want to sample from a known distribution. It could be uniform distribution, it could be Gaussian distribution, anywhere. It's from you want to sample from some known distribution, and then you want to somehow map that sample to the original image space, or actually just original sample space. So that's the whole idea behind any generative model, be it VAEs, flows, autoregressive, whatever. You just want to sample from a random distribution and then map it to the original data space. So here is the same thing. You want to sample from xt, which comes from n 0i, and then you want to somehow reverse it back to the original data here, which would be the denoising step or denoising process. And we have an assumption, which is that both processes are Markov chains. So it means that whatever you do, for example, when you're going forward, when you're adding noise, your xt only depends on xt minus 1. That is Markov assumption. And the same goes for reverse process. So when you go from xt to xt minus 1, which is the denoising step, also xt minus 1 also only depends on xt. So both processes are based on Markov. Both processes are Markov chains. So the forward process is a bit, this is a bit easier to handle. So forward processes, because everything is determinist. Actually, not everything is fixed. You don't learn anything. There is no learnable parameter involved in forward process. So forward process, you start with qx0, which is the real data distribution. So by the way, we start with q because this will be the posterior distribution, as opposed to in VAE, we had the p, and we want to approximate it with q, but here we already have q, which is the real data. And so you can imagine q being actually the p. So here qx0, it's the real data distribution. So you can sample from q probability distribution, any x0, and then what you have to do is you want to start adding a noise. So your new xt only depends on xt minus 1 because of the Markov chain, and it looks like this. So it looks like this. Basically, it's that your new sample xt comes from a normal distribution where your mu is this. This is your mu, and this is your sigma. Or actually, you can think of this as a covariance matrix. So your new xt, xt, which is a slightly noisier than your xt minus 1, comes from a distribution, normal distribution, where your mu is like this and your sigma is like this. And the beta t here is some hyperparameter. It's something that you just predetermine before you even begin your training process. So what's the intuition behind this? So if you think about bt being if you think about beta t being a very, very small scalar value, then you can imagine that xt being very, very similar to xt minus 1. For example, if you think about beta t being like 0.0001, then this term here would be almost 1. It will be like 0.1, 0.999 or something like that. So that means that your new xt will be coming from xt minus 1 times with 0.999, which means that it's almost the same thing with a very, very small amount of noise, because it will be 0.0001 I, which means that very, very small standard deviation. So that means that when your beta t is very small, it means that your xt is not so much different from xt minus 1. It's only that very small amount of noise is added to xt minus 1 to get xt. So that's it. So you can see that it's a conditional Gaussian distribution. So xt minus 1 is also comes from Gaussian distribution, because xt minus 1 depends on xt minus 2, xt minus 2 depends on xt minus 3, xt minus 4, xt minus 5, and everything is Gaussian distribution. So the whole thing is just conditional Gaussian distribution. And we call beta t variance schedule. It means that beta t, you notice that there's an index here, so which means that beta 0 is not the same as beta 1, not the same as beta 2, not the same as beta 3. So you have to set a very nice schedule to make the whole thing work. So usually what we do is this. Usually we set beta 1 to be very small, and then beta 2 a slightly larger than beta 1, all the way to beta large T, which still has to be smaller than 1. So in the original DDPM, I think, if I remember correctly, beta 1 was 0.001 or 0001. I'm not really, yeah, I think it's 0. Yeah, it was 10 to the minus 4. So it's 0.0001, and beta last T was 0.002 or something. So it's still very small. And in the original paper, they linearly increased by doing a linear scheduling, but in the follow-up papers, they do like cosine scheduling, which showed better performance. Right. So summary is that we can convert any sample to the standard Gaussian distribution without learnable parameters. So there's nothing to learn because everything, as I said, everything is fixed. So there's nothing to learn without learnable parameters by repeatedly adding small Gaussian noise. So the forward process is pretty straightforward. And one thing to note is that there's some nice property that we'll be using constantly from this page onwards. So which is that Q xt given x0 can be modeled directly. So if you think about it intuitively, xt depends on xt minus 1. I'm sorry, xt minus 1, and xt minus 1 depends on xt minus 2, all the way to xt x1 depending on x0, right? That was the Markov chain. But mathematically, if you you can derive a direct way to access xt only by depending on x0. There's a new notation. So there's alpha t, which is 1 minus beta t, and alpha bar t is a product of all the alpha i's, all the alpha t's. So it's just to make things look nicer, without too much clutter. And we'll be deriving this in the next page. But if you think about how this makes sense, is that if you can somehow derive qxt given x0 like this, then as t goes to infinity, your alpha bar t will also go to 0, because if you think about alpha i is 1 minus beta t, so it'll keep getting smaller. So if you multiply all the alphas, which is alpha bar t, then if you do it for the t going to the infinity, alpha bar t will also go to 0, which means that if alpha bar t is 0, that means that this term goes to 0 and this term goes to I, which means that your qx large T would be what? Would be almost as good as this, because this goes to 0 and this goes to I, right? So this is basically creating xt straight from x0. Originally, what you had to do is, if you wanted to get xt, you had to add small amount of noise x0 to x1, then add another small amount of noise x1 to x2, x2 to x3, x3 to x4, all the way to xt. That was the original Markov chain. But here, by mathematically deriving this, we can go straight from x0 to xt straight away. So how do we do this? Yeah, we start from here. So note that xt. Remember this. So xt given xt minus 1 was a conditional Gaussian distribution, which can be written like this, right? So if you remember the reparameterization trick, if some value is from, like a normal distribution of mu and sigma, then x is actually just mu plus sigma times e, which is e comes from 0i, right? If you remember the reparameterization trick, you can see what's happening here as well, right? Because qxt given xt minus 1 was a normal distribution with this value and this value, this being the mean and this being the standard deviation, and we have a new notation here, alpha t. So that's how we get here, and obviously epsilon t minus 1 comes from and the standard Gaussian distribution, just like here. Right. So far, so good, right? So if you have any question, just let me know, because it will be a bit mathematically involved. The whole lecture today will be a bit mathy. And if you, I don't have the time to derive all the word details. So, but if you just expand the terms and move things around and do it, so for example, here, how you go from here to here is that you simply just plug in xt minus 1 being the same as xt minus, so xt minus 1 would be xt minus 1 equals square root of alpha t minus 1 times xt minus 2 plus yada, 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 right? So blah, blah, blah. So you plug that into here. You plug that into here, and then you expand. Then you get this. You get this, right? You get this, and then you keep organizing the terms. Move the terms around, and put everything into a group. So here you move the parenthesis away, and then you get here, and then you and then you put these together to make it here, and then you come here. And then what you do is there's a bit of a trick involved. So this part you leave alone. But this part you actually merge them into a single Gaussian distribution. So for example, if you want to add two Gaussian distributions, then you have to add the standard deviation, the variances, right? So in the same manner, when you have two Gaussian distributions, epsilon t minus 2 and epsilon t minus 1, you can collapse them into a single Gaussian distribution with this this standard deviation being like this becomes this, right? So that's a bit of a trick involved. And then you keep doing that, and you keep doing that for all, you keep doing that for xt minus 2. You can plug xt minus 3 into it, and then you rearrange the terms, and then you plug xt minus 4 into it, you rearrange the term. You keep doing that all the way, and then all the way back to x0, and that's what you get here. So it means that xt can be recursively defined by all the way back to where you can define xt by x0 with a cumulative alpha bar t's and a collapsed single Gaussian distribution. So that's how you can, as a conclusion, if you can write xt as this, then it means that xt bar x0 comes from this Gaussian distribution, right? Where this is the mu and this is the standard deviation, right? So far, so good. Everybody on board? So this is very important. This red bar is very important because we'll be using this constantly in the generalized DDPM and then the classifier guidance and classifier-free guidance and all that. Yeah. So the important thing is that we can access xt straight from x0 in the forward process. Right. So the forward process is done, and we go back to we now go to the reverse process. Reverse process is a bit more tricky. So the motivation is that how do we denoise a noisy sample? So for example, we defined Q, we defined this, right? The forward process is all done, but do we know this? Is there like a known solution to qxt minus 1 given xt? Since we know this, can we somehow turn it to this, which is not easy. If you think about the Bayesian, if you use the Bayesian principle, xt minus 1, qxt minus 1 given xt can be rewritten as what? It can be written as xt minus 1 times qxt minus 1 divided by qxt, right? So this is this, right? And we do know this. This is the forward process, so we do know this, but we don't know this, and this is hard to know because it means that just distribution over all images with some level of noise, and we can't calculate this. This is intractable. So means that this is also intractable. So what do we do usually when something is intractable? We use a approximate solution. So that's where Bayesian, that's where variational inference comes in. So since this is intractable, we use a neural network to approximate xt minus 1 given xt. So this, and the good thing is that we do know that this is Gaussian distribution. This is because there's a theorem that back in the 2015 paper, the author of the original diffusion model the authors of the original diffusion paper, they proved that I'm not sure if they are the ones that proved it, but we know that theoretically, if beta t is really, really small, like small enough, it means then your forward process qt, your forward process, this is Gaussian, and your backward process, your reverse process, this is also Gaussian distribution if beta t is small enough, right? Right here. So note that this can be modeled as Gaussian because this is also Gaussian when beta t is small enough, right? So that's why we model p theta like this. So we need to, when we want to model something in the Gaussian distribution, we need to estimate the mu and the sigma. So those are the two things that we need to know when we want to model p theta as a Gaussian distribution. So that will be our objective. Learn how to estimate these two values. So how do we do this? How do we learn p theta xt minus 1 given xt? And yeah, I mean, if we can learn it, then we're good to go, because if we already have a perfect p theta xt minus 1 given xt, then we can just sample any noise from Gaussian distribution and then keep applying this function until we're satisfied with a clean realistic sample, right? Like we're gonna have to apply it like maybe 100 times or 1,000 times, because you need to denoise it very, very slightly every single time step. So we need to apply like 100, at least some 100 times, or at least some few thousand times to get a very nice picture. But at least if we have this function, then we can generate any new samples, right? So how do we train this? How do we train p theta? So immediately a lot of you would like to think about variational inference, because we're trying to approximate this intractable function using p theta, which would be modeled as a neural network. So very intuitively, variational inference would actually come to your mind. But I find it a bit easier to use Jensen's inequality rather than using variational inference. But they are actually just the same. Those two methods will give you the same objective function, but it's just more easier to. Well, for me, it was more the motivation was a bit clearer when you were using Jensen's inequality and the 2015 paper. So the DDPM came in 2020, but the original diffusion model came in 2015 by Sol-Dickstein. And the original the authors of 2015 paper actually went with the Jensen's inequality derivation rather than variational inference. So I'm actually following that. So how do we train this? So what we want to do is we want to maximize the log likelihood, right? Or actually minimize the negative log likelihood. As always, we want to maximize the likelihood of seeing our data, seeing our true data. And our distribution is Q, which is the data distribution. So that's what we have, and we start from here. So we want to maximize the log likelihood, or minimize the NLL. And you can expand your x0 to be this. So you can assume that your x0 is actually dependent on you start from xt, which is pure noise, and then you have all the so actually I have to make it a bit clearer. So this term means that x0, x1, x2, all the way to xt, which is joint distribution. So this is just easier, like a simpler way to write a joint distribution. So you can think of the column as that. So you expand your x0 to incorporate all the latent variables. Latent variables meaning like x1, x2, all the way to xt. They're all latent variables. So you expand your x0 to latent variables like this, right? And then you multiply these two, which we do know. We know q x1 to t given x0, which is the forward process, right? So we multiply these two for convenience. And then what you do is you can see this as a expectation, expectation over this. You can, because this becomes your probability density function. So integral over your probability density function is an expectation, right? So yeah, you have an expectation over this, and you can see that now you can collapse these two. You have an expectation, which is expectation over Qx0 and x0 conditioning this. So when you can collapse them like this, all by putting your log function into it, and then that's where Jensen's inequality comes in. When you put log, so if you're not familiar with Jensen's inequality, you can look it up in Wikipedia. Basically, it means that when you have a convex function and expectation convex function, when you change their places, there's a lower bound property there. So when you put log inside this, that becomes immediately, this becomes a lower, a higher, in this case, upper bound, and then you can collapse these two together. You can collapse these two together to get a single expectation, right? And then this becomes your final form here. So you just put the negative away, and then you just reverse the denominator and the numerator, and this becomes your what? Becomes your, so we can start from here. So you can compare this one, and this one, and it means that this guy is larger than this. Yeah, like this. Larger than your original NLL. Your original NLL is this guy, right? So you have an upper bound. So that becomes your variational upper bound. Or in this case, if you put the negatives away, then it will be a lower bound actually. So this will be a lower bound to your log likelihood, or an upper bound to your negative log likelihood. It's the same thing. If you're interested, you can actually go to this another way to derive variational lower bound if you have time. It'll use a you will be seeing like this, the familiar DKL KL divergence to derive the variational lower bound, but eventually you'll be ending up in the same place like this, right? So once you have this, this is a nicer form than just negative log likely, because you can actually, everything inside this term. This is basically here your forward process, and here you have a backward process that you want to model, right? So what you want to do is you want to learn this. You wanted to learn this in the beginning, right? So that's where this goes in here. So that's how. So by optimizing your variational lower bound, L loss VLB variational lower bound, you can actually learn this. This is the important part. You can actually learn this, and this is the only thing that you want to learn, because this one is actually just Gaussian distribution. So there shouldn't even be a theta here, because P(xt) comes from your Gaussian distribution, and you have all the forward process here, which is also a Gaussian distribution, and all you need to do is learn this by optimizing your variational lower bound. All right, so far so good, right? So let's further break down your variational lower bound. Actually, this is typo. I'm sorry. This should be, this should be VLB. So note that actually you can directly optimize. This function here, because as I said, the red box becomes like this, and all the terms here, so you can actually optimize them. But in the 2015 paper, in the original diffusion paper, the authors go a bit further by breaking down your LBLV, your variational lower bound, into three terms like this, three terms like this. Even though you can directly optimize this, and the reason that they go further into breaking down your variational lower bound into three components is that by doing so, you can lower the variance while training your model, training your p theta. So I'm not really exactly sure what that means, because that's an old paper, and all the papers afterwards actually just simply follows this three-term formula, the three-term framework. But the authors of the original 2015 diffusion paper says that by breaking down into these three terms, you can lower the variance while training. And I assume that what that means is that when you look at this term here, or actually just when you look at the original term here, you have to get all the latent variables, x0, x1, x2, x3, all the way to xt. So you need all the way to x1, all the way to xt in order to optimize a single term, like a single term here. You have to chain, you have to put your forward process all the way to xt to get a single chain, and then you're going to use that chain to optimize this, which involves this, And the problem is that this guy doesn't know, this p theta doesn't know where the xt's or xt-1s or like where they came from. This guy is completely oblivious to x0, where the origin of where the noisy samples came from. So I think that's somehow like making the whole optimization process very high variance and very unstable. So, but by breaking down this variation lower bound into 3 terms here, you actually see that x0 being injected here. So this actually stabilizes the optimization process, or lowers the variance, decreases the variance. So that's the whole. I think that's the whole idea, and I'm not sure if I have enough time to go through all this. But if you have time, you can actually just follow them through. I've actually written them down to make it more comprehensible. So the high level idea is that we start from here, variation lower bound, and then we change this term into all the known terms. So we know the forward, we know this, we don't know this, but we want to model the p theta. This one here, the red box, should be just pxt, which is just simply Gaussian distribution. So we start from here, and then we put because there's a logarithm, you can convert this into summation. So this part, all right, so it's a bit being cluttered. So this part can be turned into a summation, right? And then also following the original 2015 paper, the authors of the original paper treats the first term, the x0, x1 separately here. So the one final step where you go from x1 to x0, which is a reverse process, when you go from x1 to x0, the authors of the original paper treats it a bit differently than compared to all the other terms, starting from t2, t equals 2 to the capital T, and they do it so that they can avoid the edge effect. I'm not really sure what that really means. I think it's you have a whole chain of Markov chain, and when you go from 0 to 1, there's like a special property that can destroy, they can like make your optimization process harder, or make your inference harder. So they treat it a bit separately, and the 2020 DDPM paper also treats them separately by employing a separate decoder. So they have a separate decoder. The sole purpose of the decoder is to go from x1 to x0. So a special, we're doing a special treatment, right? And next one, you have to see what's happening here. From this term has become actually this term here. And the idea is that you have qxt given xt-1, which is a forward process, and you can slide in your x0 because it doesn't really matter because of the Markov property. xt only depends on xt-1, so sliding and injecting x0 doesn't make any difference. And then starting from here, you can do a Bayes you can use the Bayes principle to derive this one. So that's how you go. This is right here. Right, and then you can see you can further break this terms down into like log goes here and log goes here, right? And then there's summation here, and interestingly, if you think about this, expanding this term here, everything will cancel out except for the first part and the last part. So the summation goes away. So yeah, terms cancel each other out. And all you're left with is, so if you rearrange the terms and clean them up, all you're left with is this. And that's how you have a three terms here. So you can split the EQs into like EQ0 and EQX0 and EQX1 to T, and X1 to T can be used to turn this into a DKL divergence. Also can be used to turn this into DKL. And the last one is just last one, right? So that's how you end up with three terms here. One term is called LT, the last one, and the bunch of terms here with the summations is called LT minus 1, and the last one is called L0. And you have everything is analytically computable. So nothing is like, you don't need any like Monte Carlo simulations, you don't need any samplings. It's all just, all good to go, because DKL of two Gaussian distributions is analytically tractable. So all you have is DKL here, one DKL here, another DKL here, and both are just KL divergences between two Gaussian distributions, right? So LVLB, your variational lower bound, is broken down into three parts. And if you look at the first one, first one doesn't have any learnable parameters, because if you think about this one, this is just NOI, this is just standard Gaussian distribution, right? So if you can just remove this theta away, because there's nothing learnable here. So your LT has no learnable parameters. So in terms of optimization, you can just ignore LT. So you can just ignore LT. And if you look at L0, take a look at the L0. As I said, this is a edge case. This is where you go from 1 to 0, the final one step where you complete your denoising process and get your final actual clean sample, right? So here, the DDPM, the 2020 paper authors of the 2020 DDPM paper, they modeled this with a separate decoder derived from this special, the same Gaussian distribution. It's basically just using mean squared error. So just note, it's suffice to say that you need a separate decoder for this. So all you're left with is this one. This you need to ignore. This one is just a simple MSE. So all you're left with is LT minus 1. And LT minus 1, so this one. So this is a KL divergence between two Gaussian distributions. So this one, we do know that this is Gaussian distribution because we modeled this as a Gaussian distribution to begin with. We assumed this was Gaussian distribution anyway from the beginning. How do we know that this is also Gaussian distribution? So that's the whole point. And this also comes from the 2015 paper. But this is also Gaussian distribution. And how do we know this? How do we know that this has a form like this? So there's a lot of derivation of proof involved. So this is it. So how do we know that this thing here, how do we know that this can be rewritten as a Gaussian distribution that follows some mu and some covariance matrix? So this is the answer. So if you break this down into, again, using Bayesian principles, then you can get this one. You can get this. And then, of course, here, X0 is irrelevant because of forward process. So this becomes here. And then if you think about how this and this and this, they are all Gaussian distributions. So this is Gaussian distribution. And if you remember the nice property that we derive from here, this is also Gaussian distribution, right? So accessing XT, creating XT directly from X0, that was also Gaussian distribution following this mu and this sigma, right? So going back all the way to here. So this is Gaussian distribution. This is Gaussian distribution. Everything is Gaussian distribution. So if you think about Gaussian distribution, they're exponential terms where there's the x minus mu. Oh, there's transpose, and then there's exp and there's like a bunch of terms that the normalization terms, right? So if you think about only the inside of these three Gaussian distributions, then you can rearrange the terms like this, like this, like this. And then if you just keep rearranging the terms around and around, just have the second order terms into a single group here, second order, single group here, first order terms, single group here. And if you think about how Gaussian distributions can be rearranged into this form, then you can say that this guy indeed does follow a Gaussian distribution where you have mu and covariance that looks like this. So your mu looks like this, and your covariance looks like this. Yeah. So it's a bit involved, but the important thing is that this is actually a Gaussian distribution. So then why do we need this? Why do we need these both two to be Gaussian distribution? Because we want LT minus 1, which is DKL between this term, which is a DKL between this term and this term. If both terms were Gaussian, then it'll be analytically tractable. It'll be easier for us to solve. So that is why we want those both terms to be Gaussian. And this is actually Gaussian because we model it as Gaussian. Do we know if this is Gaussian? By going through all this gory detail, we do know it's Gaussian distribution with this this terms here. So all in all, back to the high level overview picture. We can ignore this, not relevant. This, we know that it's a KL divergence between two Gaussian terms. This we are treating as a separate decoder with MSE loss function. So we're ready to just optimize using gradient descent. Right. So before we do that, before we actually go through the gradient descent, there's one final thing. So if you look at this term here, this is KL divergence between two Gaussians. And we know that this guy is this, which comes from here, and here, So we just copy pasted it. So Q xt minus 1 given xt0 xt x0 follows Gaussian distribution like this. And we know that we want it to be this. We need a neural network to model this guy and this guy, right? For here, actually in 2020 DDPM paper, the authors actually just treat the covariance part as a constant. And it still works like a charm. Doesn't really matter. It works okay. I mean, there's a follow-up paper called Improved DDPM, which actually learns the sigma and gives you a better log likelihood and better FID. But without the sigma being learnable, without sigma being a constant, it still works okay. So in the original 2020 Ho et al. Paper, the authors treat sigma as a constant. So all you need to do is actually just learn with neural network, learn the mu of your p theta distribution, the reverse process. So we set mu theta to be this guy. So what? So right, because Q xt, this guy looks like this, and we want p theta to look like this guy because we're doing a DKL. So we can assume that your p theta's mu term would also look like this guy, So right here. Same thing. And we said that mu should be, and we said that sigma will be a constant. So all we need to do, if you look at this term, xt is given, right? Xt is given. You can derive xt from x0 because we have xt given x0. We have the direct access to xt starting from x0. So xt is fixed, alpha t is fixed, beta t is fixed, alpha bar t is fixed. All you need to do is model epsilon t, which is the noise that was added when going from xt minus 1 to xt. So all you need to do is learn, all you need to do with neural network is learn this term only. So instead of the high level picture again, so instead of your neural network modeling, your neural network should be modeling p theta, which was to model this mu and sigma, but we said that sigma should be constant, and we said that when you look at the mu in a closed form like this, all the learnable parameters should be residing inside this epsilon term only. So now your neural network is not predicting mu. Your neural network is now predicting epsilon when given t and xt, when given t, xt, when given xt and t. So when given a noisy sample xt and the time step t, your neural network should be predicting a corresponding noise epsilon, or epsilon t to be more precise. So that's what your neural network should be doing. Right. Hope everybody's not losing the high level picture so far. So, and a bit more details. So for your sigma square, for your variance, there are two choices. You can set your sigma to be beta t, or you can set your sigma to be this term here, and either options worked okay in the empirically. Either options worked okay in the 2020 DDPM paper. So you can just use whatever you want. Right. So your final form, your final optimization form for using your LT-1 would be, you'll have to actually solve DKL between two Gaussian distributions, right? So if you think about how DKL PQ, where P and Q are both Gaussian, it'll look like this. But we said that sigmas are not learnable. Sigmas are just constant here. Sigmas are just constant. So we throw them all away. And all we are left with is just here, this one. And we said that mu's we're not going to model mu's directly. We're going to model the sigmas actually. So let's look at how that happens. So if you look at this term here, so LT-1 is a KL divergence between two Gaussian distributions. And as I said, only this part remains. So only this part remains. So here we come here, right? So it's just simple MSE, basically MSE between two mu's. And the first mu is first mu. We know that first mu is this, which is this, right? So that is our first mu here. And our second mu, which is mu theta, we have it here. Right? We have it here. So we just copy paste it right here, this one. And if you rearrange the terms around, we just put all the constants outside the Euclidean distance, then all you're left with is this. So it's just simply your epsilon t, which comes from your Gaussian distribution, with your estimated epsilon being, this is your neural network should be receiving. There's a neural network. It should be receiving xt and t, and then it should be giving you epsilon t, or estimated epsilon t. And you want that epsilon t to be as similar as possible to your actual epsilon t. And that is it. That is all you need to do. Right. And yeah, actually you can rewrite this term into like this actually. Because your xt can be rewritten because your if you go all the way back, so sorry about the page. If you go all the way back, this is your xt, right? And if you rearrange the terms, then you can write this in terms of x0 equals something xt something epsilon, right? So that's what happens. That's what's happening here. That's what's happening here. So you don't even need to actually have XT. You don't even need to put your XT into your neural network. You can just simply reuse your X0 like this. But in the reality, but this is just semantically what it means. But actually, you will actually put your XT and T into your neural network to estimate your epsilon T. So here, the important thing is that if you have followed their whole derivation closely, then you know that your neural network should be receiving a dimension, a sample dimension, a sample of dimension that is the same as your image dimension, or actually this data. Let's just say that you're dealing with images. So let's just say that your image has a certain dimension, which would be like 128 by 128 by 3 or something like that, right? So your XT would be having the same dimension as this, because XT is just X with noise, right? So XT is X with noise, so it has the same dimensionality, and your epsilon T also has the same dimensionality as this. Also has the same dimension as this. So basically, what this means that your neural network should look like an autoencoder. It should receive it should accept data. It should accept sample that has the same dimensionality as data dimension, and it should output the same output that has the same dimension as the data dimension. So that is what so you have to have a certain like neural network architecture that follows the constraint. Right. If you look at, this was your final term, actually. So all you need to do is you just need to minimize this loss or minimize this loss. And you see that there's like complex term here. And what Ho et al. In 2020 DDPM paper found out is that you can just throw away all of them. You can just throw away all of them and it still works okay. Actually, it works even better with only just this guy. So that's what they found. Right. And so if you look at the sampling, if you look at the training algorithm, it is super simple. Like all the things that we've seen so far with all the complex derivation and all that, they were all necessary so that your training process can be written in 6 lines here. All those mathematical derivations and like all those like expansion and like reorganizations, you're rearranging the terms, they were all there so that you can train your neural network with only 6 steps. So step one is you sample any sample from your data distribution, just any image from your data set, and then you sample a specific time step t from a uniform distribution from like 1 to t, like t being like 1000, typically 1000. So any small t between 1 and 1000, and then you have your epsilon from a Gaussian distribution, and simply you plug them all in. You plug them all in. So you have your x0, which comes from your data distribution. You have your t, and your t, which comes from your uniform distribution, and you have your epsilon, which comes from normal distribution, and also here as well. And then you're good to go. You just minimize your function. You just minimize your loss function or MSE function so that you can train your parameter. You can update your parameters of your neural network, which should look like an autoencoder. And you do it until convergence. When you're sampling, it's a little bit different. Sampling, you have to do it gradually with taking many steps. Here, you can see that we didn't take any steps. This is a forward process. You didn't take any steps at all. Like you didn't have to go from x0, x1, x2, x3 all the way to xt. You just directly access t from a uniform distribution. But when you're sampling, when you're generating an image, you have to actually follow very close, very carefully from t all the way to large T all the way to 1. So 1000 iterations actually. Well, when T equals 1000. You sample any noise from your Gaussian distribution, and then for 1000 for loops, what you do is you sample a Z, or it could be an epsilon, doesn't really matter. You sample some noise from your Gaussian distribution, and then you plug all those into this form here, which is coming from mu theta, which is just basically x minus 1 xt, right? So your mu theta looks like this. So simply you just keep applying this equation until your xt minus xt minus 1 becomes x0, which is your, actually no, not x0. To be more technically correct, you apply this until you reach x1, and then when you reach x1, you apply the special decoder that you set aside separately. You apply your special decoder to make it into x0 one more time. So this is your generation sample. So you start from just complete noise. Doesn't look like anything, and then you keep applying your p theta x t minus 1 xt, which should follow, which is Gaussian distribution with mu theta and constant I, right? Yeah, x t minus 1, like this, right? So you just keep applying your p theta, and then you will eventually end up in a horse or a frog or a boat or a car or whatever. And note that this is unconditional. This is unconditional generation, so you don't know what you're generating. Actually, it could be a horse, it could be a cat, it could be dog, whatever. But you can see that how it is, like, gradually being denoised, being like noise is being taken out to take more forms and more forms and more forms, and eventually it'll look like a real sample. Right. So far any question before another generation stuff. You can, it also, the good thing about diffusion model is that it also works pretty well with high dimensional data like 256 cell HQ. So it looks very, very nice, right? It's almost as good as like GAN models. Like GAN models are known for their high quality, very sharp images, but they suffer from mode collapse and very unstable training. Diffusion models, they overcome those two limitations. Their training process is super, like, not as unstable as GAN. Like, this relatively much more well behaved because of all the mathematical things that we did with, breaking your variation lower bound into 3 parts, and then removing just breaking down LT-1 into into a simpler form using DKL. Like, all those things enabled a very nice, very stable optimization process. So it's not as unstable as GAN, and also it generates very diverse samples like this. So it doesn't often fall into mode collapse. So compared to GAN, like, diffusion is a way better model in that respect. But the problem is that diffusion models are slow, because when t equals 1000, you have to actually run your for loop 1000 times to make one sample. But in GAN, you don't need to run for loop. You just push your z into your into your generator, and that's it, right? So compared to GAN, DDPM is way slower. So that's one of the drawbacks. So yeah, as I said, there's improved DDPM where you don't treat your sigma or covariance matrix as a constant. You actually want to learn a diagonal covariance. You want to learn a diagonal covariance matrix. So, and the way they do it in this Nicole et al. 2021 paper is that they model covariance matrix as a interpolation between beta t and beta tilde t being this guy, and they have they show better performance in terms of like image quality and the log likelihood and that kind of stuff. Right. So far, does anybody have any question? The whole thing is very mathematical, but the important thing is that you grasp the high level idea, like the derivation and the rearranging the terms and all that. You can actually do it in your own time. The important thing is that you understand the high level ideas of why we do all this variational inference, like, and we break terms into further break down the variation lower bound into 3 terms, and then we treated each term separately, and then we further looked at the LT-1, which is a Gaussian which is a KL divergence between 2 Gaussian distributions, and then that's how we ended up having a very, very simple training algorithm like this. All right. No question. So I don't expect you to ask mathematical questions right now, but if you have any if you don't understand the high level concepts, now is the time to ask. All right, now that's a bit surprising. Maybe everybody already knows diffusion models. Right, I'm going to move on to the generalized DDPM then. So generalized DDPM is actually helpful for accelerating your generation process, because before in DDPM you had to run your for loops like thousands of times, but with generalized DDPM you can actually simplify it into, or you can take smaller number of steps, maybe a few hundred steps, or maybe even a few dozens of steps, and you can still get like not the most high quality pictures, but like reasonably okay pictures. So how do we do it? So since I only have 20 minutes left, I don't think I can go through all the like mathematical details, but let's look at the high level ideas. So DDPM suffers from slow generation. So quoting from Song et al. 2020, for example, it takes about 20 hours to sample 50,000 images of size 32 by 32 from DDPM. But in GAN, it takes less than a minute. So compared to 20 hours and less than a minute, that's like how many? Like at least 100 times faster, right? So that's the drawback of DDPM, even though it has all the nicer properties, like, diversity and stable training and the high quality pictures. It has all of that, is that it's slow. And what if the high level idea is, what if we generalize DDPM to non-Markovian chains? So here, the core idea of DDPM was that the forward process and the reverse process was that both processes were all Markov chains. It had a Markov assumption. But what if we just relax that into non-Markovian chains? Like, what would happen then? So that's the whole idea. So if we generalize DDPM into non-Markovian regime or non-Markovian framework, it turns out that we can use pre-trained DDPM. So we don't have to retrain you don't have to train another network to get a non-Markovian DDPM. You can actually reuse your pre-trained DDPM with slightly different way of sampling. So that's how, it has two benefits. One is that we can perform deterministic sampling. So deterministic sampling means that when you start from some xt in the original DDPM, because it has noise injected every single reverse process, you can just go like this way, this way, this way. Like you'll end up with different samples, right? Different samples every single time. But when you use something called DDIM using non-Markovian sampling process, then you'll always if you have a fixed xt, you'll always end up in the same place, So that gives you a deterministic sampling. And another good thing is that we can take multiple steps during sampling, so which is accelerated sampling. So by going non-Markovian, you have two benefits: deterministic sampling and multiple skipping multiple steps at the same time. Yeah. Question from Hujie Tang. During training of DDPM, why do we only sample a specific T from uniform? Actually, that's one of the benefits of going through all the mathematical details. Otherwise, so if we hadn't done that, then we would have to stick to this formula and then pick on x0 and then put x0 through all the x1, x2, x3, x4 all the way to xt, and then optimize this. But we didn't want to do that because of the high variance thing. So that's why we went into all the gory details to break it down into three parts. And then because we did that, that's why we were able to sample a single t from uniform time, just one t from 1 to 1000, and then directly optimize it. And then you can do it with, so you don't have to, you can set your you can compose your mini batch with t being 1. So you can say, so your mini batch could be like x1, x3, x5, x99, x1, 150, x5, x955, x like 800, 821, any x's from any time step, you can use them in your mini batch, and it'll actually be way more efficient when you're training your neural network, because it can look at multiple t values at the same time. So does that make sense? This is actually like a strength, not a weakness. Hopefully that answers your question. All right, I'm going to move on. Understand this. Then why don't we not set t equals 1000 directly? Then why don't we set t equals 1000? Oh, actually, you need to show your model. You need to show your p theta a lot of different x's from a lot of different time steps, or a lot of different noise levels. Actually, you can't just set your x. You can't just set your t. You cannot train your p theta only with xt's all the time. It needs to see x1, x2, x3. Eventually, by sampling for uniform distribution, your p theta will be seeing all the x's from all different kinds of noise levels. And that's how it can denoise sequentially from xt to xt minus 1 to xt minus 2 to xt minus 3 all the way to x0. Right, okay. Right, I'm seriously running out of time, so I will have to jump through all the details, actually. So yeah, we were talking about the benefits of going non-Markovian. So non-Markovian, yeah, I actually don't have enough time to actually go through this. So if you have time, you can actually take a look at it. The important thing is that the forward process is no longer forward process. Here, you model your forward process. Before it was q x1 t x0 was q x0 times all the q xt minus 1 with t equals 1 to t, right? That was original DDPM's forward process. But here you can see that it's no longer forward. This is forward, right? This is actually backward. And this is not even like complete backward, because it's conditioned on x0 at the same time. So it's completely different thing. Like, you no longer assume that your forward process is Markovian. It's not even forward process. It's something else that depends on x0. So it's kind of like if you have all the x's, if you have all the x, oh, not this one. If you have all xt minus 1 all the way to xt minus 1 all the way to x0, then it'll always have a dependency like this. Not just this, not just like this, but it'll also have all the dependencies from x0. So that's what this means. So it's completely different approach. And the good thing is that if you stick to this and then go through all the mathematical details and derivations, and then the good thing is that your direct access creating xt directly from x0 still is the exact same formulation as the original DDPM. So even though you're using completely different thing, like something that breaks the Markovian assumption altogether, but you can still arrive at the same xt even x0 that doesn't change from the original DDPM. So, and in order to do so, the authors of Generalized DDPM had to make this function exactly like this. If you make your function exactly like this, then your xt given x0 will also be the same as original DDPM. And the reverse process is also a little bit involved, so I'll just skip through that. So if you go through this like training objective and all that, it means it happens to be the training objective. It happens to be the same loss as original DDPM, even though you're using this new thing, and also this new thing. Just so happens that you don't have to train. You can just, because their loss function is the same as DDPM's loss function, you don't have to train a new model for non-Markovian DDPM. you can reuse your original DDPM and then treat that as a non-Markovian DDPM. So that's the whole idea behind this generalized DDPM. Yeah, you can use retrain DDPM. And the sampling process is a little bit different now. So the sampling process involves a noise term that looks like this. So you can actually dial up or dial down the randomness of your sampling process. So if you dial down your random noise to 0, that becomes your DDIM. If you put your sigma t equals 0, then that becomes your deterministic sampling. So this is all possible. This was all possible by assuming this non-Markovian thing. Right. Right. And also the fun thing or interesting thing is that if you set your sigma t to be exactly this form here, then this whole thing becomes DDPM's reverse process. Yeah. So it becomes exactly like DDPM. So, but this kind of like the whole like generalized DDPM is a bit something like bigger than DDPM because of the non-Markovian assumption. And so as you can see, you can set your sigma t to be this, which reverts it back to DDPM, or you can set sigma t to be 0, which makes it deterministic sampling. And by doing so, you can actually have an accelerated sampling. So I'll also have to skip through the details, but by doing accelerated sampling, what you can do is you can see that now t has become tau. So tau is the index number at which we perform a reverse process. So you don't have to go from xt to xt minus 1 to xt minus 2 and all the way to x like 2, x1, or x. You don't have to do this actually. When using accelerated sampling, you can start from xt, go straight to xt minus 2, and then t minus 4, and maybe t minus 6 and t minus 10, something like that. You can skip through. You can skip to different spots or different time steps. And the tau is used to indicate the skipping time steps. Right. So when you use this DDPM and generalized DDPM and DDIM, actually, when you set your sigma to be 0, and then you do the skipping thing, then it actually performs pretty okay. So compared to original this is the original DDPM. When you take 1,000 steps, then you get a very nice log likelihood. But when you start taking less number of steps, like instead of taking 1,000 steps, when you take 100 steps, you see immediately increasing log likelihood, or actually this is negative log likelihood. And then when you take 50 steps like this, when you take 20 steps like this, when you take 10 steps, just 100 times larger negative log likelihood. But when you use DDIM, like here, you can see that when you take 1,000 steps, 4. When you take only 10 steps, only 3 times increase. So only 3 times increase. So that's the whole the strength behind DDIM. You can set smaller number of steps. And of course, it'll give you slightly less quality image, even compared to like 1,000 steps. Like 3.17 is like lower than 4.04. So it'll give you there's like a slight trade-off. Right. So that's the accelerated sampling. And now we go to guided sampling, which is basically just conditional sampling. So we have 2 ways to do conditional sampling. One is classifier-guided sampling, and another is, it'll come later, but which is classifier-free sampling. So as you can see from the title, classifier-guided sampling requires a separate classifier. Basically, it's just as it says there, you need a separate classifier, which is right here, which is that given a noisy sample with arbitrary noise level, you need to have a classifier that can classify that noisy sample into a certain class, like 1,000 image in a class, or like 10 cipher 10 classes, something like that. So you need a separate classifier. But the good thing is that as long as you have a separate classifier, but you need to train it with different noise with samples from different noise levels. You need to train it in a special manner. But once you have it, then you can reuse your original DDPM and then guide the sampling process into sampling a specific class of your preference. You can sample only dog class or your cat class or your car class or whatever, but you still need a separate classifier. So that's the whole idea. So unfortunately, because I'm running out of time, I won't be able to go through the detail again. But the whole idea is that you need this. So you need this, a new forward process, which is conditioned not only on your previous XT, but it also is conditioned on your class, preferred class Y. So, and Y being just some one-hot representation or some token that represents a class. So, yeah, you can rewrite this. So you can, you want this. So you have a new forward process, and your reverse process would look like this, and you can rewrite it into a Bayesian form like this, and then you can see that this is, you can think of this as a normalizer. Then you have this becoming here and this becoming here, which means that you can break your reverse process into two parts, which is the original reverse process and your classifier. So as long as you have that's why, as I said, as long as you have a pre-trained classifier, you can reuse your p theta, which is already trained. You can just reuse your already pre-trained p theta with a combination of a trained classifier and then sample whatever you want. So how does it work? So how does it guarantee that it works? So yeah, okay, I won't be able to go through the detail. So the high level idea is that we said that your reverse process can be broken down into two parts: your original reverse process and your pre-trained classifier. And we know that your original reverse process follows a Gaussian distribution, where in original DDPM, sigma was just a constant, right? Then you put your log in front of it. You put your log in front of your Gaussian distribution. Then you get this guy. And then your classifier. If you expand it in a Taylor expansion form, like first order Taylor expansion, then you get this with the gradient here. So all in all, what we're trying to do is that we want to do a log likelihood model log likelihood of this guy, which gives you this, right? Which gives you this, and then this consists of two parts, which is this part this part. Okay, I need to erase some stuff. This part is this guy. This part is this guy. Maybe I can color code it differently. This guy is this part, right? So that's why you have this. That's why you have this. And then if you rearrange the terms and all around and around, then what you have is that your log likelihood of your reverse process is like this, where your z comes from your normal Gaussian distribution, where your mu is slightly changed before. So compared to here, so compared to here and here. So the original reverse process was following this, and your new classifier-guided process follows this. And the difference is that mu and here. So the new classifier-guided sampling has this sigma g, which is that g is this guy, which means that now your sampling process is guided by the gradients of your classifier. So it can adjust your reverse process in a way into the region where your classifier will be likely to classify your noisy XT into your preferred class. It could be dog, it could be cat, or whatever. So that's the whole idea behind the classifier-guided sampling, and you can see that the algorithm is pretty simple. And the drawback is that you need to have a separate classifier that is trained on noisy samples of different levels of noise. So you need to, it requires some labor. So that's classifier, and yeah. So that's classifier-guided sampling, and you can see that when you also there's a control variable. So S is a control variable as to how much you want to guide your reverse process into generating a preferred image of the preferred class. So if you increase your S, then it'll look like this. If you decrease your S, it'll look like this. So I think this is the left one, yeah. So this is when your S equals 1, and this is when your S equals 10, and your S and the preferred class is here. What is it? It's Pembroke, Welshie, Corgi. So when your S is small, it is not too constrained to generate Corgi images, but when your S is like high, when this is like high, then your reverse process is constrained or encouraged to generate Corgi-like images like this. So that's, you can see how it works in action. And so there's also classifier-guided DDIM. So this is classifier-guided DDPM. So this is classifier-guided DDPM, and you can't use this formula directly into DDIM because this whole thing can only be used for DDPM. So for DDIM, we need a special treatment, and in order to do that special treatment, you need to make a connection between DDPM and something called noise condition score matching, NCSM, which is based on long-giving dynamics. So whole gory details behind long-giving dynamics, but the important thing is that in long-giving dynamics, you need to you sample your image, you sample your samples from a score that approximates your log likelihood of your data distribution, or actually gradient of your log likelihood of your gradient distribution of your data distribution. So your score should be modeling this, and this whole thing has a pretty close connection with DDPM because this also has your this score matching network also depends on noisy samples, and your DDPM also depends on noisy samples. And yeah, I'm sorry, I apologize for describing this in a very, very high level manner, because in order to explain this is going to be another whole class. So, but suffice to say that there's a close connection between DDPM, and noise condition score matching, or long-giving dynamics to be more accurate. And based on that, drawing intuition from this connection between the two, you can write a new sampling process which looks like this. So that now your classifier guidance can be used for DDIM as well. So not only for DDPM, also DDIM. So the reason that we're talking about this is because in classifier-free guidance, this still will be used. This whole concept of using, estimating your epsilon with this classifier guidance here. Oh, sorry, not here. Classifier guidance here with your gradient of your log likelihood is still being used in classifier-free guidance. So yeah, and yeah, I'll have to jump through the details, but if you're interested, please look at this part. Please look at this part carefully, because it makes a connection between long-giving dynamics and DDPM, and how this gradient of your log likelihood can be seen as can be seen as a epsilon that we model, that we learn from the that we learn from your p theta xt minus 1 xt. So the whole DDPM's reverse process is all about learning epsilon, right? And by learning that epsilon, what you're actually doing is you're kind of learning a gradient of your log likelihood, and gradient of your log likelihood is used for sampling realistic samples using long-giving dynamics. So that's where the connection is. So in classifier-free guidance, this whole thing is used again. The gradient of your log likelihood can be made connection to your epsilon, or can be may connect to your reverse process, actually, reverse process. And this whole thing is used in generating samples in a conditional manner, even without pre-trained classifier. So that is why it's called classifier-free guidance. So far, in classifier-guided sampling, we needed a special pre-trained classifier, right? So that was true for classifier-guided DDIM as well. But in here, classifier-free guidance, you don't need a pre-trained you don't need a pre-trained classifier. You can just train one neural network for diffusion for diffusion, and then you can use that for conditionally generating any sample you want from your preferred class. So, and the way that you do it is that so this is your class Y, and now your epsilon depends not only on X, T, and T, but it also depends on your class, your preferred class, or your wanted class, desired class. And it can be seen as a linear combination between class conditioned epsilon and class unconditional epsilon. So I'm jumping through all the derivations. I'm just giving you the conclusion. By training a single this network here, neural network that depends on XT, T, and the class, you can use it to do a linear combination between conditional E and conditional epsilon and unconditional epsilon, and use it as a linear combination to guide your sampling process to generate samples of your desired class. So how does it work? So this guided noise is a linear combination of conditioned and unconditioned noise, conditioned noise, unconditioned noise. So that means that, do we need to train this and this separately? Do we need like two neural networks for this and for this? That is no. The answer is no. We can train both this conditional and unconditional with a single neural network. And the trick is that sometimes you train with a null class, random sample, null class. So you give Y equals like 0, like null class, 10% of the training time. So that, just like this. So your autoencoder, or actually the authors, all the people use neural net, something called UNet, to train your epsilon EXT T, or in this case epsilon XT T and Y. So they use something called UNet, which looks like this, kind of looks like an autoencoder of images. Like there's a compression stage, and then there's decompression stage, and then there's residual connections, skip connections at every like different residual blocks or resonant blocks. So that's what UNet is. And because it has the same input and output dimension, it is a perfect fit for training your epsilon function. And you can train just one UNet you can just train one UNet for this conditional and unconditional. Some by 10% of the time, you set your Y equals null so that you can train this unconditional. And then when you're doing reverse process, you can use a linear combination between the two to generate a sample that you want. And how does it work? It works like this. So you can see that if you rearrange the linear combination into this, then it seems like there's a difference between your conditional epsilon and your unconditional noise. So conditional noise, unconditional noise, and then there's this thing is and this term is a delta term. It's a delta. It's a difference between the conditional and unconditional. So it kind of looks like this here, guiding your sampling process into the preferred, into using the gradient signal from your classifier. It's kind of like that, kind of analogous to that. So that's how you can use a single UNet as an implicit classifier to generate samples from your desired class. Yeah, this is all high level, but if you go through this like in a step-by-step manner, you'll understand that the high level idea all makes sense, and the final code is very, very simple. Like the derivation is a bit involved, but the final code and the final learning implementation, the model implementation is pretty straightforward and pretty easy. Right, so if you when you use classifier-free guidance, what happens when you use? So there's also still you have this omega term, which used to be this S term here, So when you have the omega term to control your reverse process. So when your omega is 0, it's non-guided, then your neural network, your diffusion model generates all kinds of things. But when your omega is 1.0, it starts to generate. Actually, this part is always unconditional. This part is this is unconditional. This is unconditional. This should be a Malamute. Malamute, the dog. And when your omega is 0, doesn't really. I mean, it still generates because when omega is 0, when omega is 0, this term survives, and this is conditional, still conditional. So it kind of generates like dogs, but it's not always Malamutes. It contains like this noisy samples like this, or like this doesn't look like a Malamute either. Like this is not a Malamute, right? But when you increase your omega to 1, then this starts to look more Malamute, like, or they're like mostly Malamute examples, right? And if you increase omega to 3, then we are pretty sure it's all Malamute. But then you see that you start losing your diversity because you're guiding your diffusion model to generate very, very Malamute-like samples only. So it's kind of like sticking to a very small range of samples. So that's how you can that's how you can control how much fidelity you want by increasing or decreasing your omega. Right. So that's it. So it has been like a very, very 1.5 hour crash course on DDPMs, and try to cover a lot of things. But these will, but you need to understand all this to understand DALI 2, actually. DALI 2 and diffusion, stable diffusion, imagine, they're all based on like DDPM, DDIM, generalized DDPMs, and classifier-free guidance and all that. They're all used heavily in DALI 2 as a stable diffusion imagine. So if you want to understand them, you need to understand the concepts. And hopefully this has been at least a good primer for that. I mean, you'll need to go through the details to actually really understand. So if you have time, please go through the slides again, step by step, and try to derive by yourself with your own hand. And this Thursday you'll be implementing DDPM. You won't go through like classifier-free and classifier-free guidance or classifier guidance and that kind of stuff. You'll be implementing DDPM only, but hopefully that will be a good practice for you. Right. I'm sorry for going a bit overboard. I'm 13 minutes late. So before we end, do you have any question? All right, I'm gonna wait like 5 seconds before we end. Okay, cool. No question. If you do have any question, please post them on Classroom, and please do attend this Thursday's practice session, because just by looking at the mathematical formula, it's probably not gonna like sit well into your brain. All right. And the next week next week's gonna be the final class with multimodal models, specifically using text and images. So I'll see you guys next Tuesday. All right. Thank you guys. Bye-bye.
감사합니다.
네, 감사합니다.